Welcome to this presentation on UNIX Inode Allocation, focusing on ialloc, iget, and the Superblock. We'll explore how the kernel allocates, caches, and protects inodes to avoid file system chaos. This is aimed at systems programmers, OS students, and SREs. By the end, you'll learn inode fundamentals, the difference between on-disk and in-core structures, core algorithms like iget and ialloc, optimizations such as Superblock caching and remembered inodes, concurrency handling for race conditions and locking, and the inode lifecycle including freeing mechanisms and tradeoffs. Think of inodes as the backbone of UNIX file systems. They manage everything from files to directories. Let's dive in to make these concepts clear and straightforward. Let's start with the basics. What is an inode? It's a key data structure in UNIX file systems that describes objects like files, directories, or devices. It holds all metadata except the file name and actual data content, things like permissions, owner IDs, size, timestamps, and pointers to data blocks. Inodes are stored in a big linear array on disk, each with a unique number. The kernel caches active ones in memory as, in core, inodes, adding extra fields for management like reference counts, locks, and status flags. An inode is free if its mode field is 0. Remember, file names live in directory blocks, mapping names to inode numbers. This setup keeps things efficient: disk for persistence, memory for speed. Now, onto iget. This function retrieves a known inode by its device and number, often after a directory lookup via name. The goal is to get a locked, in-memory copy for safe modifications. It starts with a cache lookup. Lock the hash table, search for the inode using hash, dev, ino. If found, check if it's locked. If yes, sleep until unlocked and retry. If not, increment the reference count, lock it, and return. This is the fast path. Avoiding disk I/O hash lookups make retrieval quick, locking prevents concurrent issues, and ref counting ensures the inode isn't reclaimed mid-use. Simple yet crucial for performance. Continuing with iget. If the inode isn't in cache, we hit the slow path. Allocate a new in-memory slot, read the disk block containing the inode using bread, copy the data into the structure. Set ref count to 1, mark it locked, insert into the hash table, and return. Overall, iget ensures exclusive access. Key mechanisms: fast hash checks, sleeping on locks for fairness, and ref counting to manage memory. This balances speed. Most hits are cache-based, with reliability, only reading disk when needed. In code, it's from kernel, fs, inode. C, showing UNIX's elegant simplicity. Shifting to ialloc, used when creating new files or directories, like open with o_create or mkdir. It finds a free inode quickly without scanning the entire disk. Goal: pop a free inode number from the Superblock cache. Start by locking the Superblock for exclusive access. If the cache, s_ninode, isn't empty, pop the top number, unlock, then use iget to load it. Verify it's free, i_mode == 0, to catch races. If good, initialize with mode, link count 1, current user ID, etc. This LIFO cache is 1, fast. Superblock lock prevents double allocation, and race checks ensure safety. Building on ialloc, after popping and loading via iget, if the mode is 0, set up the new inode. Assign mode, set nlink to 1, UID, gid to current user, clear blocks, update timestamps. Commit by writing to disk immediately, then return. If the cache was empty, trigger a slow path. Scan disk from the remembered inode onward, refill the cache with up to 100 free inodes, update the remembered pointer to avoid rescanning used areas. This minimizes I/O critical. Verification catches if another process grabbed it, ensuring no overlaps. It's memory fast most times, with writes only on commit. Let's talk optimization. The Superblock caches free inodes to minimize disk I/O. It holds an array s_inode 100 as a stack of free numbers plus s_ninode count. Also, s_remembered_inode points to the highest checked inode for efficient refills. When cache empties, lock Superblock, scan from remembered point, add freeze to cache until full or end of disk, update pointer. This is LIFO for quick pops. Benefits: 1. Allocations usually, avoids repetitive scans. The physical disk inode table is linear, with colors showing used, free, scan status. Smart caching makes common operations blazing fast while keeping consistency. Concurrency is tricky. Enter race conditions like the phantom free inode problem. Without locks, process A pops inode 100, context switches, B refills cache seeing 100 free, adds it, A marks it allocated. Then C grabs 100 again, causing corruption. UNIX mitigates with Superblock locking during allocation, refill, type verification, double-check disk mode after load, and immediate writes to shrink race windows. Timeline shows how locking serializes access. These defenses ensure safety under high load, preventing duplicates or data loss. It's a balance. Locks add overhead but avert chaos. Now, ifree, called when an inode's ref count hits 0 and links are 0, file deleted. Goal, mark it free on disk, possibly cache for reuse. Lock Superblock, set die_mode to 0, write to disk immediately, increment total free count. If cache has space, less than 100, push the number to s_inode stack. This immediate write prevents reuse races. Superblock cache adds for quick future iallocs. If full, check if this inode is lower than remembered. Update to optimize scans. Simple, but ensures prompt reclamation. Wrapping ifree, in code, after disk update, case A, space, assign to s_inode, s_inode++. Case B, full, if ino less than s_remembered_inode, set it there. Don't drop low numbers that could speed refills. Unlock Superblock. Dropped inodes are still free on disk, just not cached. Mechanisms, immediate writes for consistency, cache for hits, remembered for optimization. From kernel, fs, ialloc. C, it's about reclaiming efficiently without stalling. Tradeoff, small cache size limits bloat but requires occasional scans. Anally, analyzing the architecture, UNIX balances speed, safety, consistency. Tradeoffs, Superblock cache, fast allocations but risk stale refs, mitigated by checks. Remembered inode, reduces I/O but biases to higher numbers. Locking, prevents corruption but bottlenecks under load. Immediate writes, narrows races but adds sync I/O cost. Core summary, linear disk inodes, free via mode equals 0. iget, ialloc via Superblock, caching as high-speed buffer, defensive checks assume races happen. Philosophy, correctness first, cache for common fast paths. This design influenced modern file systems, elegant and robust. Thanks for watching.